Okay, so now let's go to chapter 3, the fabrication of single crystal silicon. So we know that there are 3 types of the solid. So that is amorphous, polycrystal, and monocrystal, or single crystal. For the semiconductor devices, so we mainly use the single crystal silicon because single crystal silicon is easier to control the properties. And then the amorphous or the polycrystal materials. For example, by doing the doping, we can control the electronic properties of the single crystal material better than the amorphous or polycrystal silicon. So amorphous silicon is used for the solar cells, but not very high. The solar cell is still mainly used single crystal material. Some solar cell, maybe 10% of the market use the amorphous silicon, and also for the displays. For the display, we have the large area. So the amorphous silicon can be the film can be deposited by the plasma enhanced chemical vapor deposition method. For the PECVD, we can deposit over a very large surface area. So this is good for the display. So to make the called TFT, thin film transistor. So polycrystal is used for the MOSFET gate, but we know now that nowadays we use HKMG. This is the high K material metal gate. So nowadays we use metal gate, no longer polycrystal silicon gate. So today the wafer size is 12 inch for the production, 300 millimeter. So here is the MOSFET we have talked about. So we have the single crystal silicon substrate. So we have the natural spacer is amorphous silicon, and this one. So this is the amorphous nitride. The gate oxide is also amorphous, and the silicide we have the titanium silicide, and also polycrystal silicon. This is the polycrystalline. So for the silicon, we know we have the cubic structure. So now we look at a simple, a brief introduction to the crystal structure. I know you are familiar with this from your other courses. So what we have here is the lattice. So we have the cubic lattice. For the cubic lattice, so we can define the planes and the directions. So the direction is defined as the component in the X, Y, and Z unit. For instance, this is the 100 direction. 10 is along the X direction. This is along the Z direction. This is 001. Y direction is 001, 0. So this one is the 110 direction, because if you draw the component here, x-axis is 1. If you draw here, y-axis is also 1, but no component along the z-axis. So this is the 111. If you draw it here, x, y, z is all 1. So this is the direction. So the plane is defined by the so-called Miller index. Is the reciprocal of the intercept of the plane with x, y, and z axis. For example, this red color here is the 100 plane. So intersect with x equal to 1 is parallel to the y-axis. So the intersection is infinity, no intersection. And also the plane is also parallel to the z-axis. So the intercept is also infinity, parallel, so it's also infinity. So then we have this 1 over 1 over infinity, 1 over infinity, which equal to 100 plane. So this is the 100 plane. For this one is the 111 plane. And this one is, the red color here is 110 plane, because the intercept is along the 1 x-axis, 1 and z-axis. So this plane here is perpendicular to the, so 1, this is the y-axis, x-axis. With the z-axis, because this is parallel to the z-axis, it will never meet. So it will intercept. It will intercept at infinity. So you have the 1, 1, infinity. I will do the reciprocal. You got 1 over 1 over 1 over infinity. You go 1, 1, 0. For any plane, LMN, it is always perpendicular to the direction LMN. For example, you can look at here. So the 111 direction is perpendicular to this 111 plane, and 110 direction perpendicular to this 110 plane. 100 direction is perpendicular to this plane. So this is very important because, for example, if I ask you to calculate the angle between two planes, for instance, the angle between this 110 plane and this 110 plane, then you can calculate the angle between the two directions. So that means I build the angle between two planes. For example, we have the one plane is the plane we use L1, M1, and 1. This is one plane. Another plane is L2, M2, N2. So we have two planes. And we want to know the angle between the two planes. So we can calculate the angle between the two lines. This line 1. So the angle between the two lines. So how to calculate the angle between the two lines? So we can do this way. If we have the vector A and the vector B, so A equal to this one, and vector B equal to this one, the angle between the two lines can be calculated by this method. So A equal to A times B cosine theta. So we know about this. So we know AB dot equal to this one. Then we can find out the angle between the two lines. So we have seen before, silicon has the face-centered cubic. Face-centered cubic. We have two of them merged face-centered cubic, which offset by A/4. So that means if this one is 0, 0, 0, then this one, as we have learned in chapter 1, equal to A/4, A/4, A/4. So there's a coordinate for this one. It's offset by A/4 in the XY direction. So the defect, so in the ideal single crystal, there is no defect, but in reality, there is defect. We have the point defect, a line defect, which is mainly dislocations, and planar defect, stacking fault. So stacking fault, this actual line, stacking fault. Green boundaries is also plane, and surfaces. Bulk defect, like crack, void, pores, precipitate. Those are the bulk, like a precipitate, void, a crack. Those are the bulk defect. So now let's look at the point defect. So point defect is more important because it determines the dopant diffusion in the material. So we have the substitutional point defect. This one, for example, can be boron. If it's boron, this is doping. This is the interstitial point defect. This one is vacancy. So this one is the Frankel type defect. It is the pair of the interstitial and the vacancy. So now let's look at how to grow single crystal silicons. So the silicon is grown from the material comes from the sand. So we know that the main component for the sand is silicon dioxide, and then we make a metallurgical grade of silicon out of the sand. This one is 98% purity. From this one, we purify it to make electronics grade silicon. This one is many less purity. So now let's look at how to the sand. We know it's very cheap. It's very cheap. So the wafer is about for the wafer, I would say for the 4-inch, is about $10 per wafer. For the 8-inch, it will be $20 per wafer. So this is the wafer, the cost for the wafer. For the chips, each CPU is like $100 each CPU. So first, let's look at how to convert silicon dioxide, sand, how to convert sand into the silicon. So we need something to take away the oxygen. That means we need something reducing agent. So in this case, we use carbon. So high temperature, we mix sand and the carbon, then we form the silicon and the CO. So this one is gas, is pumped away, so leave behind a liquid silicon. So at this temperature, the silicon is liquid. So this is what we have. It's called, so this silicon here is the metallurgical grade of silicon. It has 98% purity. This one is produced a large quantity. You see, this is like 900,000 tons per year per annum. So 900,000 tons per year. So it mainly used to make aluminum alloy and also to the silicon rubber. The very small percent of this silicon is used to make silicon wafers. So here are the impurities. So we have the aluminum, and we have the iron. This one is very bad. This transition metal impurity usually is very bad for the electronic devices. We also have many other impurities. So now we need to purify it. We need to purify this metallurgical grade silicon. For the purification, we can use distillation to purify a material. For example, if we have a mixture of water and ethanol, so you can use the distillation for the purification, because water and ethanol, so they have different vapor pressure, different boiling temperature. So the purification will work for liquid. So first we need to convert silicon into liquid. Then what do? We use a hydrochloric gas and silicon to form trichlorosilane. And this one, hydrogen is gone, so we can collect trichlorosilane. At the room temperature, so this one is become a liquid. But the boiling temperature is only 32 degrees. So we can do the multiple distillation to collect this gas vapor, to collect this gas. Then we convert it back into the silicon. So we use the hydrogen gas to convert it back into the silicon. So you can see that this chemical reaction is the inverse of this chemical reaction. So this will happen if you keep removing the product. Then you can make sure the chemical reaction goes to the right side. So you form the silicon. So this is how you get the very pure, high pure single crystal silicon. So now let's look at, so now we have the very pure silicon. So now we want to make it, so this one is polycrystalline. So we make single crystal silicon. So this method is developed by, we have two ways to make single crystal silicon. The one is called the Trochowski, the other one is called the float zone. So this is CZ, the other one is the float zone, FZ. So this one is discovered by the Trochowski in 1916. He is a Polish chemist. So what he did, so he had a tin, a molten. So we know that the tin can be easily melted. So he had a tin. So he had a molten tin. Then he dropped his pen. So he dropped his pen in the tin. Then he pulled it back. Then he found out there is something. He found out there's something, a thin thread of the solidified tin hanging from the nib of the pen. He verified that, so this tin here is single crystal. This one is single crystal. So this is the way called a CZ method. So effectively, so we dip a single crystal material into the molten material. Then we pull out to form the single crystal. So the material here, maybe I'm not sure, maybe carbon. So what's the material for the pen? This can be carbon or some other materials. It's the seed. So this has the seed material. So here are the details of the CZ method. So it's used to make the silicon, gallium arsenide, and indium phosphate. Those are the, as we know, it's called the 3,5 semiconductor materials. So we have the electronic grade silicon broke into small pieces and put in this silicon oxide container. In the argon environment, so we can heat the container to 1,440 1417 degrees. So this is the melting temperature of silicon. So the silicon gets melted. We can also add some dopant into the melt. For example, we add some boron. We add some boron into the melt, or some phosphorus in the melt. So then we get, when we grow the silicon, it will be doped. So then we have the seed. So this single crystal seed. So this one is the single crystal seed. It's dipped into the melt. Then you pour out slowly. So the silicon will follow the pour out. Then it become a solidified, and single. So this one is single crystal silicon. So it is rotated. You can see we have the rotation. In order to have the circular cross section. So otherwise there will be a facet. But now when we do the rotation, we have the circular cross section. So the balls, it's called the balls. This word is called the balls. The ball can be very big, can be 100 kilograms. There will be a lot of oxygen coming from this one. So this container here is silicon dioxide. We have a lot of oxygen here. And also carbon from the heating, from the graphite heating, will come into the silicon, and they have this amount of the impurity. So here is the schematic for the CZ growth method. So we have the carbon come from here. So this one is carbon. So the carbon impurity. So the carbon impurity comes from here. This is called the graphite susceptor. So we have the RF coil. So this one is for the heating. So how come the coil can be heat? This is like a microwave oven for cooking. If you put some conducting material like a metal, if you put a metal spoon in the microwave oven, it will be heated up very, very fast. It may even have spark. So don't put the metal in the microwave oven. So here, so when we have the coil, we know that. So when we have the coil, I pass the current, so we generate magnetic field. Is that we generate magnetic field. So when we have radio frequency, high frequency coil, so we have the frequency is omega. So we have this term. We have something like this. So the partial B over T is not zero when we have the high frequency radio frequency. And we know that, so this one equal to, if you remember electromagnetism you have learned, this one changing magnetic field give you electrical field. So we have electrical field, there will be current flow. So when this is called eddy current. So we have the current. So this one connecting, graphite conductor. So we have the current. So when we have the current, so we have the heating. So we have the heating, IR square Joule heating. So that's why this is how we heat up this silicon by this RF coil. Here are the photos of the CZ growth method. You can see we can make really, really big bowl. So this is called bowl. So this word is called a bowl. If we can have hundreds of kilograms of both single crystal silicon. So as we have mentioned, so there is oxygen from the silicon dioxide crucible and the carbon from the heating element from the susceptor, graphite susceptor. So oxygen 10 to the power 18 and carbon 10 to the power 16. So this is a large amount, but usually this is not a big problem because the oxygen here, it will, during the process we have the high temperature process. When we have high temperature process, it will form a silicon oxide. The silicon oxide will not harm the device so much. The oxygen maybe, you may think this may be a dopant. We have extra electrons, so we have this may be like a dopant. Could be a dopant, but when from the silicon dioxide, it's no longer a dopant. It's from the precipitate, it's no longer a dopant. So actually, this silicon oxide, the oxygen, can be very useful for getting rid of the impurity. So this is called internal gathering. We will see the internal gathering in chapter 4. So what do you see here? The white color here is actually silicon dioxide nanoparticles. So we will see this in next chapter. So now we want to know the growth rate, how far we can grow. So obviously, the faster you pull it out, so the pulling speed, the faster you pull out, it will become a smaller diameter of the bowl, right? So the faster you pull out, the smaller diameter of this bowl. So now we want to figure out the relationship between the pull rate and crystal diameter. Pull rate and crystal diameter. So what do we have here? So we assume that the freezing occurs between the isotherm X1 and X2. So the freezing occurs in this region. So here isotherm means same. Iso means same temperature. So at this cross section here, so this is the isothermal 1, temperature 1, and at this cross section here, this isothermal X2. Isothermal means this cross section has the same temperature. Now we figure out the heat from the liquid, through this cross this section and across here and move out. So we have this heat from here and move out. So the latent heat of the fusion. So when the silicon gets crystallized, it has a large latent heat. So this term, latent heat, is called latent heat of fusion. dm over dt. M is the mass. M is how many gram. This is M. T is time. So this is the latent heat. Apply the heat from here. This heat from here. So this is the heat connected from metal to the crystal. So the heat connection is given by thermal conductivity, temperature gradient A1. So this dx1. This is 1 because this is the isothermal X1. This is the heat. This is the heat getting into here. This one should be equal to the heat connected out. So this one Ks, thermal conductivity over the solid material, temperature gradient over the X2. So this is 2, X2. Temperature gradient times the area. So this is the equation. This is the balance of the heat. But we know that, so the heat from here to here, this one should be small, because this latent heat will keep to raise the temperature to generate the heat. So the temperature between here and here, the temperature gradient here should be small, because even though this part is cold, there are lots of heat generated here. So not much heat flow from here to here. So we can ignore this term. So dm over dt, so this term here, dm over dt. The mass change, the mass amount of freezing per unit time. So dm over dt is related to the pull rate. As you can imagine, as you can see clearly, the dm over dt equals to pull rate. So this is the pull rate, Vp, times A is the cross-section area, N is the density. So we know that. So normally we use rho as the density, but in this text, we have the rho as already resistivity. So here we use N as the density. So dm over dt equals to V, the pulling rate, An. So then we put this one Van here. So this one Van, so pull rate. So dm over dt equals to Van. Arrow here, and this term we cut it out, and we can find out. Finally get this term. So this one, so we need to find out the temperature gradient at this cross section. So in order to find out the temperature gradient, we need to know how much the heat gets dissipated out. This is done by the radiation. So the heat loss is mainly done by the radiation. So the radiation, so we have this called Stefan-Boltzmann law. So the radiation, the heat is the surface area per area. This is the surface area. We talk about the area of this belt. So 2 pi r dx. So this is the surface. This is the dx. This is dx. So this is the surface area. Sigma is the Boltzmann constant. So this is, we know Kb is also a Boltzmann constant, but this one is the Boltzmann constant for the black body radiation. So epsilon is the emittivity of the surface. For the perfect black body, epsilon equal to 1. For gray body, epsilon is less than 1. So it's proportional to the T power 4. So this is the black body radiation. So actually, so the heat loss from our body is also mainly by the black body radiation. So if we have the surface area of a person, so the surface area of a person is, we can consider like a 2 square meters. So then we have this sigma. We have temperature about, this is about 30 degrees. Our body temperature minus, so we radiate the heat. The environment also radiate the heat to our body. The environment, we have this equal to 20 degrees. So this is the room temperature. Room temperature, environment also radiate the heat to our body. So the difference, every time the 2 square centimeter, they put in sigma. This one give you 120 watt. So that means, our body can radiate 120 watts of the heat. So we know that in one day we need, typical people, we need 2,000 kilocalorie of the food. We need this amount of energy from food, right? A normal person needs 2,000 kilocalorie from food. So 1 calorie equal to 4.2 joule. Then you can, this one give you 10 to the power 7 joule per day. So this is 10 to the power 7 joule per day. Divided by how many seconds per day? We get about, how many seconds per day? We get 116 watt. 116 watt. So this is the energy we take 116 watt. We take 116 watt energy from the food today. So you can see, so this number here is comparable to this number here. So that means a large amount of our body heat is lost by this black body radiation. So what do we eat? In that become the black body radiation, get heat lost. So now, so we have this equation here. So we need to find out dt over dx. So another equation we know, the heat conduction along the surface is given by Q is equal to thermal conductivity of the solid, pi r square is the cross-section area dt over dx. So we have those two equations. So here we have, from here you can move the dx to the left, so you have the dq over dx. So you move the dx to the left side. So here you have dq over dx. So we should also do dq over dx here as well. So this is what we will do. So we do the dq over dx, and we see how much it becomes on the right side. So dq over dx equal to the first term is this part. This one become this one. So this is the first term. Then we have the second term, dk over dx. So we can ignore the change of the thermal conductivity along the x. So we ignore this term. So this one, then this one become this one. So here we have the dq over dx. So here we also have dq over dx. Then they are together. We have this equation here. So now we have another term, the Ks. So this term varies roughly at 1 over T. Thermal conductivity varies at 1 over T. So if the Km is the thermal conductivity at the melting point, then Ks equal to this term. Then we put this one into here, Ks here into here, so we get this equation. But this equation is not obvious how to solve it. To solve it, if you want to solve it, you can assume that T equal to A x plus B power gamma. You can assume this is the answer. So this is the solution for this one. Then you do the derivation 5 times, 2 times. You put this in. Finally, you can find out A and B and gamma. Then you can find out the Tx. When you know the Tx, you can figure out the dt over dx. You can find out dt over dx. Then you get the maximum pulling rate, because the maximum pulling rate is given by dt over dx here. Dt over dx here. But this is the maximum pulling rate is given by, in the end, is given by this formula. So here you can see, so the larger the diameter, smaller the pulling rate. So this makes sense. So L is the latent heat, N is the density. So now we can have an example to do a little calculation. So we want to know the maximum pull rate for 6-inch wafer. So then we use this formula here. So the latent heat is given back here. So this is the latent heat, 430 calorie per gram. The density is 2.328 gram per cubic centimeter. So 2 sigma Boltzmann constant is given by, this is the Boltzmann constant. The emissivity is 0.55. Thermal conductivity is 0.048 calorie per second per centimeter per Kelvin. Temperature, melting temperature, this is the melting temperature. Radius, 6-inch, is 7.62 centimeter. So now we have the unit here, work, ERG, and the calorie. So we need to convert calorie to work, or work to calorie. So this then is given by this formula here. So what is work? So calorie we know. So 1. So this is what we know about it, right? 4.2 joule. So what is work? So ERG is the CDS unit. So C means centimeter, gram, second. So ERG is energy in the CDS. It's called the centimeter, gram, second unit, this unit. So we know that the joule is the MKS. So joule is energy for the MKS unit. So this is the meter, kilogram a second. So how to convert the joule and work? So we know that energy is given by, so this is energy, right? 1 over 2 mv squared. So the energy unit is mv squared. So 1 work equal to m, we use the gram, v squared. V is centimeter per second squared. So this is what equal to 1 over 1,000 kilogram times 1 over 100 meter per second square. So 1 centimeter equal to 1 over 100 meter. So 1 gram equal to 1 over 1,000 kilogram. Then we know this. So we have totally 10 to the power 7. Minus 7. It will be minus 7 joule. So you can see, so 1 calorie equal to 4.2 joule. And the 1 work equal to 10 to the power minus 7 joule. So to convert it, so 1 work equal to, so this one divided by 4.2. Then you get the calorie, right? You get the calorie. So 10 to the power 7 divided by 4.2 is given by this number. So then you have calorie here, the calorie here, the calorie here. So this work cuts out this work. So the calorie here cuts out this calorie here. So in the end, you get a centimeter per second, which equal to 23.6 centimeter per hour. This is the pulling rate. To pull the 1 meter long of the ball will need 4 hours. Okay, thank you.